On July 1st, 2025, a telescope in the Chilean desert picked up a faint dot of light moving against the background stars. Within hours, astronomers around the world realized what they were looking at. It was not from here, not from our solar system, not from our star, not from anything within trillions of miles of Earth. It was a frozen relic from another star system entirely, traveling at 137,000 miles per hour on a trajectory so extreme that its orbital eccentricity of 6.14 is the highest ever recorded for any object passing through our solar system. To put that in context, anything with an eccentricity above 1 is not bound by the sun's gravity. This object was at 6.14. It was screaming through our neighborhood on a path so steep that it will never return. It is only the third interstellar object that humanity has ever detected. The first was 1I/Oumuamua in 2017, a strange elongated body that showed no cometary activity and left scientists arguing for years about what it even was. The second was 2I/Borisov in 2019, a comet that looked surprisingly similar to our own solar system's comets. This third one, designated 3I/Atlas, turned out to be something different from both. And when the James Webb Space Telescope turned its infrared eye on it and read its chemistry directly, what came back surprised researchers in ways they are still working through. Because the chemical fingerprint of this object does not match anything in our solar system, its deuterium to hydrogen ratio is more than 30 times higher than any comet native to our sun. It carries the scars of billions of years of galactic cosmic ray bombardment etched into its molecular structure, and its estimated age, based on its trajectory traced backward through the galaxy, is between 3 and 11 billion years. Our sun is 4.6 billion years old. This object may be older than our entire solar system. Stay with me because this is the story of the first interstellar visitor we were actually ready for, and what it is teaching us about the universe beyond our star has never been possible before. I am narrator name, and this is channel name. Subscribe now if you want more stories like this, because what we are learning from this object right now is rewriting the textbooks on planet formation, and we are covering every piece of it. Let me walk you through what actually happened, because the discovery itself was a milestone in how we do astronomy. On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS, operating from its station at Rio Hurtado in Chile, flagged a faint moving object. Within hours, pre-discovery detections were identified in existing data from the Zwicky Transient Facility and from earlier ATLAS images, pushing the observation arc back to late May. When astronomers plotted the orbit using those combined observations, the numbers were immediately extraordinary, an eccentricity of approximately 6.15, a velocity at infinity of roughly 58 kilometers per second, an inclination of 175 degrees, meaning it was coming in nearly opposite to the direction most objects in our solar system travel. There was no ambiguity. This object had originated far beyond our solar system and was passing through on a one-time visit. Within days, the International Astronomical Union confirmed its designation as 3I/Atlas, the third recognized interstellar object in human history. But here is why this discovery was fundamentally different from the first two. When 1I/Oumuamua was spotted in October 2017, it was already on its way out. It had already passed closest to the sun. Astronomers had only a few weeks to study it before it faded beyond the reach of even the largest telescopes. They got almost no compositional data. The object showed no cometary tail, no outgassing that instruments could detect, and its strange, elongated shape and unexplained non-gravitational acceleration sparked theories ranging from hydrogen ice to, famously, the suggestion by Harvard astronomer Avi Loeb that it might be an artificial object. The scientific community remains divided on Oumuamua to this day because the data was simply too limited to settle anything. When 2I/Borisov arrived in 2019, the situation was better. It was clearly a comet with a visible coma and tail. Astronomers had more time to observe it, but Webb had not yet launched, and the instruments available could only resolve its composition in broad strokes. What they found was that Borisov looked surprisingly like a solar system comet, rich in carbon monoxide, leading some researchers to suggest it formed in conditions similar to the cold outer regions of our own protoplanetary disk. When 3I/Atlas was discovered on July 1st, 2025, for the first time in history, astronomers caught an interstellar object on its way in, well before perihelion, with the most powerful suite of telescopes ever assembled, already operational and ready to observe it. The Vera C. Rubin Observatory had just begun operations and had actually captured the object in survey images as early as June 24th, a week before anyone knew what it was. The James Webb Space Telescope was fully calibrated and available. The Hubble Space Telescope was operational. ESA turned interplanetary spacecraft, Mars Express, the ExoMars Trace Gas Orbiter, and the Jupiter Icy Moons Explorer, JUICE, toward the object to observe it from multiple vantage points across the solar system. NASA's TESS satellite found pre-discovery data showing the comet was already active by May 7th at a distance of 6.4 astronomical units from the Sun. The SOHO Solar Observatory caught it as it passed through perihelion in late October. For the first time, an interstellar visitor was studied by an armada of instruments from every angle, across months of observation, using technology that did not exist when the first two arrived. The scientific harvest from that campaign is still being published. Here is where the chemistry starts telling a story that reaches far beyond a single comet. In August 2025, Webb captured its first spectrum of 3I/Atlas. Martin Cordner, a cometary ice researcher at NASA's Goddard Space Flight Center who led the Webb observation team, said afterward that when he loaded up the spectrum, he was blown away. The data showed carbon dioxide, water, carbon monoxide, carbonyl sulfide, and water ice being released as the comet heated on its approach to the Sun. That alone was significant. A far richer chemical inventory than anything detected on Oumuamua and a distinctly different volatile profile from Borisov. But what made it genuinely extraordinary was what came next. In December 2025, after the comet had passed perihelion and its icy surface had been thoroughly heated by the Sun, Webb detected methane in the coma. Methane is what scientists call a hypervolatile ice. It sublimates at extremely low temperatures, which means it can only survive on objects that have been kept extraordinarily cold for extraordinarily long periods. Detecting it on a comet that had already passed closest to the Sun and was being heated significantly meant that methane was locked deep inside the nucleus, sealed beneath layers of less volatile material, and only now being exposed as the surface eroded away. That storage mechanism tells researchers something about how cold and how undisturbed the interior of this object has been for most of its existence. If you are the kind of person who stays for the real science instead of clicking away at the first complicated detail, drop a like right now because it genuinely helps this kind of content reach the people who want to hear it. But the most striking chemical finding involves deuterium, the heavy isotope of hydrogen. Every water molecule contains hydrogen. In some water molecules, one of the hydrogen atoms is replaced by deuterium, which is hydrogen with an extra neutron. The ratio of deuterium to regular hydrogen in a comet's water tells scientists about the conditions under which that ice formed and what has happened to it since. Solar system comets have a characteristic deuterium to hydrogen ratio. 3I/Atlas does not match it. Its D/H ratio is more than 30 times higher than any comet in our solar system, 30 times. That number is not a small deviation. It is a different category entirely. Researchers analyzing the data have proposed that this extreme enrichment is the signature of billions of years of exposure to galactic cosmic rays. High-energy particles streaming through interstellar space produced by distant supernova explosions and other violent events across the galaxy have been bombarding this object for its entire journey between star systems. Over billions of years, those impacts gradually altered the isotopic ratios in its ice, building up deuterium at rates that no process inside a planetary system could replicate. One research team described this as a paradigm shift. They argued that long residence interstellar objects primarily reveal cosmic ray-processed material rather than pristine material from their original formation environment. In other words, what Webb is reading in this comet's chemistry is not just the fingerprint of the alien star system where it was born. It is the fingerprint of the journey itself, billions of years of wandering through the galaxy, irradiated by the death screams of distant stars. The object carries both histories at once, where it came from, and everything that happened to it on the way here. Tracing the object's trajectory backward through the galaxy, researchers determined that its path aligns with the thick disk of the Milky Way, a region populated by older stars. This suggests the object may have wandered through interstellar space for millions, possibly hundreds of millions, possibly billions of years before encountering our solar system. The estimated kinematic age is between 3 and 11 billion years. Our entire solar system formed 4.6 billion years ago. This frozen chunk of ice and dust may have been drifting through the galaxy since before our sun even ignited. Now here is why this matters beyond the object itself. Every comet in our solar system formed from the same disk of gas and dust that built our planets. Studying them tells us about our own origins, but studying an interstellar comet tells us about someone else's origins. The ice is inside 3I/Atlas condensed in a protoplanetary disk around a different star, under different conditions, with different chemistry. Comparing those ices to what we find in our own comets gives researchers a direct measurement of how planet formation varies from one star system to another, something that was purely theoretical before interstellar objects were detected. Cordner said it himself. Interstellar comets give us the opportunity to reach out across space and time through the galaxy, to study close up the planet forming regions of other star systems. That is not an exaggeration. That is a literal description of what this data provides. A laboratory sample from another star's planetary nursery, delivered to our doorstep by gravity and time, readable by instruments we built within the last 5 years. And the Hubble data from late 2025 and early 2026 added one more piece. Post-perihelion observations allowed scientists to separate the faint glow of the solid nucleus from its bright coma for the first time. The refined diameter came in at approximately 2.6 kilometers, making 3I/Atlas significantly larger than 2I/Borisov and far more massive than Oumuamua. It survived its passage around the sun intact. It did not disintegrate. Whatever this object is made of, it held together through the closest encounter with a star it has likely had in billions of years. Here is the part that shifts the scale. 3I/Atlas is extraordinary, but it is also, according to the scientists studying it, a preview. Before 3I was discovered, the detection of interstellar objects was a matter of luck. Oumuamua was caught on the way out. Borisov was spotted with relatively modest instruments. The gap between the first detection in 2017 and the third in 2025 was 8 years, but the tools available now are fundamentally different from what existed even 5 years ago. The Vera C. Rubin Observatory, which captured prediscovery images of 3I/Atlas during its commissioning phase, is designed to photograph the entire visible sky every few nights and is specifically optimized to detect faint, fast-moving objects. Current projections estimate that Rubin may identify dozens to hundreds of interstellar objects during its 10-year operational life. The era of waiting 8 years for the next visitor may already be over. The SETI Institute's Dr. Duncan Steele described the shift bluntly. Interstellar objects are no longer rare curiosities. They are becoming a critical tool for understanding the processes shaping planetary systems beyond our own. Every one that passes through gives us a data point we cannot get any other way. A direct chemical sample from another star's formation history, delivered to our instruments by the mechanics of gravity and time. Here is what I want you to take away from all of this. In July of 2025, a telescope in Chile caught a faint dot of light that turned out to be a frozen messenger from another star system. It was traveling at 137,000 miles per hour on a trajectory so steep it will never return. It may be older than our sun. Its chemistry does not match anything in our solar system. It carries the isotopic scars of billions of years of galactic cosmic ray bombardment etched into its ice. And for the first time in history, we were ready for it. Webb read its molecules. Hubble measured its nucleus. JUICE and Mars Express tracked it from across the solar system. Rubin caught it before anyone knew what it was. And what all of those instruments found is that the universe is delivering samples from other star systems directly to us, and we finally have the tools to read them. 3I/Atlas is already heading back out into the dark. It will not return. But the data it left behind is still being analyzed, still producing papers, still rewriting what we thought we knew about how planetary systems form across the galaxy. And if the projections for Rubin hold, the next one may already be on its way in. The era of interstellar astronomy is not coming. It has arrived. And 3I/Atlas was the announcement. If this kind of real, verified, research-grounded science is what you come here for, subscribe right now and turn on notifications. Rubin is scanning the sky every few nights. Webb is standing by. The next interstellar visitor could be detected at any time, and when it is, you are going to want to have already understood what you are watching. Drop a comment with what surprised you most and share this with someone who needs to hear it, because this story deserves a far bigger audience than it is getting. Thanks for watching, and I will see you in the next one.